Good morning. As you now know, my name is Gianluca Cusatis. I'm chairing the EMI 2013 conference. There are a few announcements that I have to make before we start the morning plenary session. The first announcement is that the lunch break will be a little bit longer, 15 minutes longer, and that will push everything by 15 minutes. Okay, so the afternoon session will start at 1:30 as opposed to 1:15, and everything will shift, the breaks will shift, everything will shift. Okay, we'll post this information on the room, and this was done to address some of the shortcomings we had yesterday at lunch break. So that's one thing. The second thing, in the Lewis room where we have breakfast and lunch, there is also the second poster session. We had the poster session yesterday with 20 posters. We have another poster session today with about the same number of posters. And so please go there while you're enjoying your coffee or your bagel. Look at those posters and vote for them. You know, tonight we have the banquet and we recognize the best two posters. There is a table in the room with a box, and you can just cast your vote for the poster that you like. The third thing is tonight we have, of course, the banquet. The banquet is not in this facility. The banquet is at the Arlington Hotel. It's about 5 minutes, 10 minutes walking from here. So if you need direction, just please see whoever is at the registration desk, and they can help you. With this, I think I'm done with what I had to say, so we can start our morning plenary lecture, and I would like to ask Professor Chen to take over. He will chair this session. Please.
Hey, good morning. I'm Jim Chen from, I don't know if it's working. I'm Jim Chen from Louisiana State University. It's my pleasure to introduce Professor Robert Tony Dalrymple from Johns Hopkins University. He's the leading expert in wave mechanics, inertial hydrodynamics, and coastal engineering in the world. He received his bachelor's degree from Dartmouth College, a master's degree from University of Hawaii, a lot of surfing there, and also PhD degree from University of Florida. He has been working on the development of a code, open source software using a smooth particle hydrodynamics approach, a meshless approach, to simulate violent flows, especially related to coastal engineering, but also can be used for fluid impacts on structures or fluid and structure interaction. So please join me in welcoming Dr. Tony Dalrymple.
Thanks, Jen. Good morning. What I'd like to talk about is smooth particle hydrodynamics and its application to free surface flows. Smooth particle hydrodynamics has been around as a numerical method for a long time. It was developed in astrophysics to model the evolution of galaxies and impacts of bolides on planets and so forth. So it's been used in an application where there are no real boundary conditions to worry about, but a lot of bodies that have to be taken into account. And since 1994, it's been applied to fluid flow problems. And in about 2000, I started looking into the method. And so this has been a long, slow development of numerical models. And so what you're going to hear is a little bit of a history of the model as it's been applied to fluid flow in my circumstances. So the goal was to develop an engineering tool based on this astrophysics model or this numerical method and apply it to violent free surface flows. The word violent I put in there recently, and I think it was to attract a bigger audience, but the flows are going to be, some will be violent, some will be rather mundane, but breaking waves, for example, will be violent. So the topics will be things like dam breaks, breaking waves, near-shore circulation, that's the rip currents and longshore currents that you feel at the beach, tsunamis, so there's violence, and impact problems, more violence. During our course of working on SPH, we released all of the codes open source, and the first code that we came up with was physics. You notice the SPH with the ISIX attached. We weren't very original in how we named our code. That was the best we could come up with. But this is an open source code that was originally developed for serial machines in Fortran. It's been on the web for about 5 years now and has continued to be developed in lots of different applications, so from serial code to parallel code, the use of Riemann invariants, and other kinds of improvements to the codes, including GPU applications. But I joined up with a dissident group of coders and moved to a separate branch of the code called GPU SPH, and this is the code I'll be talking about. The nice thing about GPU SPH is it runs on graphics cards. So this presentation is being run from my Mac Pro laptop. The Mac Pros, the recent ones, have 384 processors in the graphics card, so it's a good-sized cluster machine. We have real-time visualization, so when the model's running, you see open source, or you see the OpenGL windows displaying your code as it's running, so you know if you've made a mistake and you know how the code is developing. The other important point is it's a mesh-free Lagrangian method, and it's being developed by a consortium called the Athos Consortium, and it's a bunch of people in the US, France, and Italy primarily. Smooth particle hydrodynamics, as we use it, is developed for a weakly compressible flow. There are incompressible versions of SPH. The trade-off is if you do the incompressible version, you have to solve a Poisson equation for pressure. If you use the weakly compressible and keep it weakly compressible so that it looks like incompressible, then you use an equation of state rather than having to solve a Poisson equation. And so in that sense, it's faster. The problem is that when you have weakly compressible, you have acoustic waves in the model, and your time steps are dictated by the acoustic waves. But what we have is, if you think about it, we have a domain. We irregularly place nodes in the domain. So instead of rectangular mesh or three-dimensional mesh or however you mesh your numerical model, these are irregularly spaced particles. Each particle, each node can be considered like a representative fluid particle, so it has mass. And it'll also carry the characteristics of the flow. It'll carry density, the velocities will be associated with the particles, and so forth. So all the fluid particles move with the nodes that move with the fluid. So that's the advantage of SPH, is that it's a Lagrangian method, mesh-free, and the mesh is constantly reforming as time goes by. So some of the parameters here, we have the mass mi for each particle. And since we keep all the particles in the computation, then the mass is automatically conserved. It's a compressible model, so the volume of each nodal point will change as the density changes. But it won't change very much because we're only weakly compressible. The mathematics, as originally developed by Monahan, is based on, well, now I've described it as kind of a weighted interpolation. If you have a whole bunch of nodes and you have values of something on these nodes and you want to know the precise value at a point, you just sample all the nodes in a weighted fashion. You can think of like moving least squares or radial basis functions, some kind of interpolation scheme, and you have a formula that looks like this. Monahan thought of it in the continuous fashion that this basis function would basically be a delta function in the continuous domain, and so that in the continuous domain this would be exact. The advantage of the SPH method is, this is my own pointer, and I can't even use my own pointer, sorry. The advantage is that we use this method when we compute the gradients. Remember, we have irregularly spaced points. To compute gradients in a finite difference scheme would be very difficult because you'd have to worry about the spacing between all the particles. But starting from the first boxed equation, going to the second by integration by parts, you can show that the gradient is basically the gradient of this weighting function, and the weighting function is an analytical function. So Monahan started using cubic splines. We use the Wendland kernel, which is a quintic polynomial function of compact support. The h that you see in this equation is the size of the footprint. So we have a circle of radius 2h is the footprint of this weighting function, so that the contributions to this sum are particles in the neighborhood of a given particle 2h away or less. So just to give you just an overview again, here's our irregularly spaced points, here's our weighting function, and so here's a circle of 2h, so this is the size of the footprint of the weighting function. So the contribution to a variable such as velocity or density at this point would be based on sampling the neighboring points. Typically that's about 80 nodal points that get sampled. And then we have boundaries. As opposed to the astrophysical problem, we have boundaries, and there are lots of different ways to treat boundary conditions, including just having particles on the boundary. So remember, it's slightly compressible and Lagrangian. So when we get to equations, we take the standard fluid equations, take the ones that you like. In compressible version, we need a conservation of mass, so we have the density and the velocity. And this equation, conservation of momentum, there are total derivatives on the left because it's a Lagrangian scheme, so convective terms are not to be worried about. We have a gradient of pressure. We have a viscosity term of some form. I just show it this way, but any type of viscosity term that you would like, and then a gravitational acceleration. And then finally, here's our equation of state. So if you know the density, you know the pressure. So that's the advantage of the weakly compressible scheme. So that's very fast to compute. But the problem is that we have a sound speed, c sub s. So there are sound waves that go through the model, particularly when we start the model, because you assign the particle positions irregularly, and you have kind of a shock startup. And so the sound waves have to abate. But the thing that I'm looking at, so dam breaks or water wave propagation, the speed of sound is not an important variable. So in fact, we actually slow the speed of sound down because we don't want to compute at the actual speed of sound because our time steps would be very small. So we slow the speed of sound down such that it's only 10 times the velocities that we expect in the model. And that's not giving too much compressibility to the problem and accurately representing wave motion or dam break flows and so forth. So for engineering flows, except for impact problems and except for things like water hammer or other problems when sound speed is important, we can get away with that trick. So then we take our continuous equations and cast them into particulate form, and we do that by taking the weighting function, which is analytical, multiplying it by our equations, integrating over the domain, and in most cases neglecting the boundary effects because the kernel has limited support, so the boundaries are far away, so we can forget them. At the boundaries, this is no longer true, and we have to worry about boundary terms. And there's some interesting work being done now, including in the Athos project, where the effects of boundaries, the boundary integrals are included. So here's the resulting particle form. So we have density, velocity, and here's how we move our particles. So we calculate the velocity with time stepping, and then we time step our positions. And so with every time step, we update the density, the velocities, and the positions of all the particles, and then we move on. I talked about the equation of state, and the requirement of 10 times the maximum velocity expected in the model for the sound speed gives you a low Mach number, so it's weakly compressible. And then you can choose the viscosity that you would like to use. The nice thing about it is at the free surface, unless surface tension is important, we don't do anything for a free surface condition. We treat it as just zero pressure at the surface. We don't have to do any Lagrangian surface following algorithms as you do with other numerical methods for free surface flows. So Monahan in '94 was the first to apply SPH to free surface flows. Here's his about 1,000 particle representation of a dam break, and there's a little ski jump here, and the water goes over the ski jump. And he did water waves. So this is about 1,000 particles, and he has a beach, and yet he's got plunging breakers in his water waves. So you can't see it because of the scale, but these maybe 2 or 3 particles just plunge over and make a plunging breaker. So very low resolution model, but still getting the dynamics of the physical problem. So let's talk about GPUs for a second. So I mentioned my laptop with 384 streaming processors on it that you can access each one to do the math in a massively parallel way. NVIDIA is one of the 2 video card makers that is pushing the state of the art in getting the number of processors on a video card higher and higher in response to all those gamers that I used to think were wasting their time playing video games, but in fact they're driving science when they're doing that. So if you look at this card, which is less than $4,000 and fits on a reasonably current workstation, you could put 3 in a workstation easily, as long as it has a PCIe bus. Less than $4,000, you have almost 2,700 streaming processors on that card, which you can use in single precision or double precision. Single precision, which we can actually do our computations in single precision, we're almost at 4 teraflops on this card. So this is a supercomputer for a poor man's budget. Here's an example of multi-GPU, so a dam break, a bunch of pillars in the way, and the different colors represent the different GPUs doing the computation. So there's a trade-off of the fluid particles between GPUs and so forth. And so what we're working on now is we have multi-GPU code, and now we're working on cluster GPU codes. In Katrina, you remember that the flood walls failed in New Orleans. Here's an example with a high-resolution dam break instead of a low-resolution dam break. And what you may not have seen in this, there's the flood wall failing instantaneously, 3 circular buildings here, or cubicle buildings, and then you see the massive wave hitting the buildings, a run-up on the buildings, and the splash. So that's the advantage of not worrying about tracking free surface. I recently had a visitor from China, Wu Jinsong. So what he did was dam break into a city. So it's a little bit hard to see on this slide, but here's a city. The interesting thing is he's got stairwells going down to subways, and you have a dam break that's going to occur right here. So the flooding will be this block of water flooding into the city, and from the top you see the building layout. So there's sort of a wall of buildings and then following buildings behind, and then the dam break occurs, and then if we go down here, it's gone through the first row of houses and started down the stairs, and then you can see the flooding as it goes in the underground passageways, but through the structures as well. Recently, last year, we added Open Dynamics Engine. So this is an open source library for objects and how they're related with hinges and solid bodies dynamics. And so Here we have, this is just a simple application. This is one of our test codes in the model as we have it on the web. And you can see the floating objects and how they interact with a fixed object. That's what it looks like on your laptop when you run it. So let's leave dam breaks and talk about waves. That's what I do. This was 1 million particles. So this is waves in a wave tank. Everything is two-dimensional, and yet almost immediately as the waves leave the wave paddle, you see three-dimensional effects as the waves break and the bores propagate across the surf zone, and you notice a lot of turbulence and free surface scarring and so forth. So clearly, a lot of 3D instabilities are developing as they do in nature. So we'll look at a case of, this was our case where we had the floating object with a wave. And so in this movie, what you see is a wave maker off screen to the right, generating a big wave. And we have this floating ball that, as the wave pulls back, it makes a negative wave and pulls the ball in. And then as the wave plunges, you see the wave go over the top, and the object pops out and surfs. The interesting thing is, as the wave breaks, it actually bounces, the plunger bounces, and leaves behind all of this three-dimensional structure. In fact, reverse braking. The waves actually break backwards here. And then each subsequent wave, you see the wave hit, bounce up, and bounce again. And then as the wave moves forward with the bore, you see tremendous three-dimensional turbulence in this region. And red, as you saw, is higher velocity. So this is the same problem looking at the middle. One of the nice things about SPH is every particle is numbered, and we're tracking each particle. So when you do this, particle 0 is down in this lower corner, and particle 3,240,000, et cetera, is up in this corner. And so you have massive Lagrangian tracking for trajectories. And of course, you can see all of the turbulence in the braking process, and you saw the splash up of the wave as it splashes up and generates all the turbulent vortices in this region. The interesting thing is this is a transient problem because there's only 3 waves, but every braking wave gave a different answer inside the surf zone. The other thing to note is that there's a circulation setting up here because this should have been red and now it's blue, and that's the bottom water moving up. So in the tank, there's this wave averaged kind of circulation being set up within 3 waves. So let's talk a little bit about splash up. This is a wave breaking on a beach. You notice a lot of pre-existing turbulence in the plunger as it goes over, then it hits and bounces up. This is the splash up right here. So the interesting thing about splash up is it shouldn't splash up if you think about it, because of the fact that if you, in fluid mechanics, we teach that if you have a jet hitting a wall, it runs along the wall. If you have a stationary jet, it penetrates into a fluid, and yet we have waves and the plunging jet bounces. So the question is, what does it take to bounce a jet? Jim Duncan at University of Maryland wondered that as well, and so he did a bunch of experiments where he had a towing carriage and a wave tank and had a moving jet, and said, can I bounce that moving jet? And in fact, what he got was, as time advances in this photograph, what you see is the jet penetrating, it's moving to the left at 15 centimeters per second. It's creating a cavity as it penetrates, and then because it's moving, it moves into the side of the cavity that it created, and then the jet kind of falls apart, a lot of bubbles and trained. Here is a one-phase SPH that we did many years ago. So here's the jet entering the fluid. It looks similar to this. You have the same characteristic shape here. So we're replicating the experiment well. So that doesn't answer the question. So how do you bounce a jet? Is you move it rapidly. And Duncan couldn't move it rapidly in his wave tank, but in the model you can. So basically these plunging jets are moving at the wave speed, and that's enough to get them to bounce. So one of the things I was supposed to point out to you is that if you watch the water level in the wave tank experiments, the mean water level changed at the shoreline, and that's called wave setup. And so we noticed that when we were doing the experiments that we were getting setup, and then the question is, can we get other wave averaged quantities? I mean, if you're getting set up, that implies that the wave momentum is being represented well, and it turns out that's true. And the energy is being propagated correctly and so forth. So at the shoreline, when you have waves breaking at the shoreline, the momentum that the waves are bringing to the shoreline dissipates because of the breaking process, so we need forces to counter the change in momentum. So what are the forces? Mean water level changes, so the water level goes up. Or if the waves are approaching the beach obliquely, this momentum is causing a flow along the beach, which creates an opposing shear force, the bottom shear stress. So the decrease in wave momentum is balanced by bottom frictional resistance in the case of longshore flows. So the question is, can we represent that as well? So, you know, the model looks like it's doing waves well. Will it do nearshore circulation? And so here's an experiment performed in Denmark. There was a bar that covered most of a tank. So the waves are created over here. The waves propagated over a bar, but there's a deep section, the rip channel in this location, and then a beach over here. So it's a little bit of a trough behind the bar. And so the waves are going from right to left and breaking on the bar and breaking on the beach. So here's what it looks like when you use SPH. The first time I saw this result, which was the day before a conference when I had to show it, I was amazed at all of the features that this in fact reveals. And for example, in the shoaling region, the waves get higher, so the waves shoal, the waves break. They can be plunging breakers or spilling breakers. So that part we knew. In here, you notice that the wavelengths are very short. There's a nonlinear phenomenon called harmonic generation that you see in shallow water, and so the harmonics of the large waves are breaking or separating and propagating independently. And so we have harmonic generation here. We get a higher water level in the shore region, which then drives a flow going offshore, and it creates a rip current. The waves encountering the rip current experience wave current interaction. They're now on an opposing current, and so they steepen and they slow. And so you get some wave turning caused by the wave current interaction. So a lot of wave effects are in this picture that we didn't anticipate, and we're more than excited to see. So if we look at the result in the wave average sense, so let's average over a wave period and look at the mean flows that these breaking waves that you just saw create. And so again, in this picture, the waves are coming from the right, propagating across the domain in this direction. They're breaking over the bar. And what you see is because of the mean water level setups and so forth caused by the decreasing momentum flux of the breaking waves, you see that you set up a circulation cell over the bar. There's another cell that's set up inside the trough region, and then probably little smaller ones in the corners as well. And so these are wave average results. We take the SPH results, which are Lagrangian. We interpolate them onto an Eulerian grid for this purpose, and then average over the wave period, and then average over the depth to get the wave average flows. We can also track the trajectories, and so you can follow different water particles as they move about in the circulation system. So now SPH is doing circulation. That was a happy result. And then, so then the question is, are we getting all the turbulence of the breaking waves correct? And that's what we're looking at now. So The other day we heard about Q criteria for looking at coherent vortical structures. We use the lambda 2 criteria, slightly different method. But basically what we're looking at is for swirling flows and where they occur. And so here's one picture of the waves in that experiment breaking, and we detect in this gray color with the lambda 2 that there's a lot of vorticity in this region. If we then cut the domain horizontally in a sheet and look down on that sheet and look at vertical vorticity, what we find is all along the wavefront, we have a lot of vorticity of different sign all along the wavefront. So remember, everything is started out 2D till it hit the breaking region, and then, but the 3D that we see here is far smaller scale than any 3D in the bathymetry. So these are instabilities in the breaking process creating these structures. And for many years in the coastal engineering community, we've talked about obliquely descending eddies. So as a wave breaks and passes, what we see is the turbulent cloud of bubbles being drawn down into the water column behind the wave as the wave propagates off towards the shore. And the question was always, where did these tornadoes come from? And what was the cause? And so this looks like these could be the obliquely descending eddies starting right at the breaker. And then this picture, you might have a little hard time seeing it, but what you see is instead of individual tornadoes, what we see is that these are horseshoe vortices. So what we have is a patch of turbulence in the breaking wave. If we're moving with a wave, what we see is a mean flow going by in the opposite direction, which draws these horseshoe vortices out of the turbulent cloud in the breaking wave and draws them behind further and further as the wave propagates. And so you see that, in fact, instead of individual tornadoes going down for the obliquely descending eddies, it looks like they're probably horseshoes, vortices being drawn out. And you can look at individual particles. So if you're looking where the obliquely descending eddies would occur, what you do see is if you follow a particle, in fact, it does cycle down into the water column. Whereas in front of the wave, this particle just surfs along with it like the ball did. So let's move to tsunamis. Solitary waves were the first analog. So a theoretical wave to be an analog for a tsunami. So here's a solitary wave propagating by. But the interesting thing is that the same types of structures are left behind when a tsunami propagates, a spilling tsunami like this. And so there are a lot of stories of ships and so forth just spinning around after a tsunami goes by. Some of that might be associated with the vorticity that's left by the breaking process. Our tsunami in this case is rather small, as you may have noticed. So, computer scale tsunamis. This is some comparisons of wave elevations. I haven't shown you any validation yet, so this is some validation, but experimental solitary wave versus the same wave that you just saw. These are water surface elevations going down the tank and looking at it at a variety of different locations. It's the same wave, lots of different locations. And on the left, you see the simulation, and on the right, you see the actual experiment. So if we look at these structures in detail, what you see is here's the wave at one instant in time. You can label some of these structures, and in time, what you see is the evolution of the structure into these horseshoe-like structures. Again, this is the solitary wave. If we look at one of those horseshoe-like structures, and then what we did was drop a vertical plane down and then look at it from the front of the wave, and what you see with vorticity is counter-rotating. So these horseshoes are pulled out behind the wave, and they're rotating like this. And then what they do is they start moving down into the water column. So now take a look at this. This is supposed, for the wave people in the crowd, this should wake you up. This is the advantage of modern technology. These are pictures. There are a lot of pictures on the web now taken with GoPro cameras. These are underwater cameras. Unfortunately, I don't have one, and I'm not in Hawaii. But what people are doing is going under breaking waves, mostly to look at surfers. And you may have noticed the surfer here. You're looking at the bottom of the surfboard. You can see the daggers right in here, the fins. So which is the front of the wave and which is the back of the wave? This is a plunging breaker, so you're getting a big air tube, and this is the surfer's tube, right? So the wave is breaking in this direction. There's a big hollow air core inside. The front of the wave is to the left, sorry. Front of the wave is over here. This is the back of the wave. The surfer's riding in the tube on the back of the wave, but he's inside the tube, obviously. But look at these amazing structures. So I first saw these about a year or two ago, and I'm still flabbergasted by the difference in sizes, and they're coming out of the plunge point, and perhaps where the plunge point is going into the water, injecting air, and then the pre-existing turbulence in the plunger perhaps is spawning all of these things that ring around the tube. And there's obviously an instability because they blow up when they get onto the backside of the wave. But they're sort of periodic along the wave. They're very prevalent. You can find hundreds of pictures like this on the web with all the people showing off their GoPro camera results. But it's phenomenal. And unfortunately, it's on my to-do list, so I'm not going to show you any results because this is what I would like to be able to model, but you can imagine what the resolution is that you have to resolve these vortices. So this is a teaser because I don't have any results for that. So going back to tsunamis, you may recognize what this is a cartoon of. This is done with a solitary wave. But what we have is an offshore breakwater. This is kind of a half of a symmetric looking plant. And so an offshore breakwater and a solitary wave coming in. There's a cliff in front of the plant structure and then the flow around the structure. So the ability to model the free surface flows is critical. This is another comparison to laboratory results. This is the Okushiri Island tsunami, devastating tsunami in 1993 in Japan. And there was a valley called Monai Valley about in this region where there was very catastrophic run-up. And so there was a laboratory study done. And so this is, instead of generating the waves with a solitary wave, it's generated by a wave maker that replicates the actual wave created in the laboratory. And so these are the kind of results we get and others get. The dots are the experimental data, and the blue line is ours, and the others are other models, including another SPH model. But basically, the wave arrival is modeled by all very well. And then back here, we didn't have any wave maker information, so everybody's got noise back there. But good representation of the tsunami. Now, I always wanted to be a rocket scientist, so here was my chance. This is the Orion space capsule being tested at Langley Air Force Base, or Langley what? It's not Air Force Base, Langley Research Facility, Langley. What they have is a big swimming pool. They have a prototype of the Orion space capsule. This is on YouTube, so you can find it if you want it. And you'll notice that what they did was just swing the capsule and drop it. The trick is that the capsule is supposed to come down on 3 parachutes, and there's going to be a wind, so it's going to be translating as well as falling. And then depending on how the chutes are hooked up and if they all 3 deploy, it has a certain orientation as it hits the water. So, let's see if we can get this one to go again. So this orientation that they have now is a pretty flat angle as it hits. It's not a big angle. And so it skips. And then there's a huge wave that goes over the top. So here's what we do. This actual shape of the capsule. And it hits, and then the big wave goes right over the top. Now, for the astronauts, this is good. They're upright, and the landing was successful. If this happens, that is to say there's a larger angle of attack, this is not good for the astronauts because they don't want to be upside down. Furthermore, surprisingly enough, the capsule will sink because there's an air gap between the heat shield and the command module itself. So they're actually worried about it sinking, and so ending either upside down or on its side is a bad thing. So then the question is, what are the angles of attack, and what are the speeds at which it will land upright or flip over? And so, of course, in a model, we can do this very easily. So we did about 60 runs and fit a plane through regions where the blue dots represent angles of pitch of the capsule and wind speeds. So there are no numbers here. We weren't allowed to release numbers, but a lot of them are wind speeds so high that you wouldn't want to land the astronauts in that case anyway. But there are speeds where you can actually roll the capsule several times if it's going fast enough and the angle is steep enough. So, but all of that was done without waves, and of course there are waves in the ocean. They want to land in the ocean. Here's what happens when there's a big wave, so that worked out well. But then there's this big wave maker, watch out. And then it ends up on the beach like driftwood. But the point is that doing that, this thing was all done with a flat water surface, and with waves, then you've got a random surface. So then what is the actual surface where the astronauts will be upright when the capsule hits? Another example is wave energy devices, natural application. And so here's a pretty large scale, this is a person, large scale wave energy device that is supposed to move back and forth with the waves with this free swinging object. And Billy Edge at North Carolina State University has been using GPU SPH to model this behavior. And so this is a rather small scale model, as you see. It's three-dimensional. And looking at the behavior of this object, the interesting thing is he's actually modeling the chain. So there's like 25 chain links that he's modeled with the Open Dynamics engine. And you can see how the buoy is going up and down, lifting the chain off the bottom, stretching or straightening the chain and so forth as this responds to waves. So, in conclusion, I hope I convinced you that SPH is a good tool for free surface flows. We're using it quite a bit for looking at water wave phenomena. GPUs I didn't talk much about. These vastly accelerate the computations by 2 orders of magnitude. And basically what we do is we set up the problem on the CPUs, we push all the data up onto the graphics card, and then we send commands to the graphics card to do all the computations. And then when we want to see partial answers or the final answer, we pass back the data. So all the heavy-duty number crunching is done on the GPU and on Kepler cards where we have those almost 2,700 processors. With GPUs, the drawback of GPUs, there's no free lunch. The drawback is there's not a lot of data storage on the video cards because they don't need them for video games. For us, that's not a problem. For some computations, it may be that you have too much storage at each node, and this might not work. It might not be a technique to work for you. But if it works, if particularly if you can work in single precision, it's super fast. If it's double precision, you have a factor of 2 kind of hit. But other than that, it's a cheap way to do high-performance computing in your office. And then the Open Dynamics engine is basically saved us a lot of computing for floating objects and hinged objects and so forth. It's a very nice, powerful library to add other features to the model. So GPU-SPH is a model that I think in a year or so will be a reasonable engineering tool. We're still making improvements to things such as doubling precision, doubling the storage capabilities and all of these other things, multi-fluid flows and so forth. So it's evolving as I speak, but I hope you enjoyed hearing about it. Thank you.
Yeah. The floor is open for questions. First of all, I would like to ask our panelist, Professor Don Liu, to ask a question. Don.
Thank you very much, Professor Dalrymple, for sharing your pioneering knowledge and exciting demonstrations. We really enjoyed it. I have 4 questions in 3 different categories. I thought maybe it's better for me to go one by one.
Okay.
Instead of throwing towards a bunch of questions, you forget about them. So my first question is about the one slide on the equation, the mass conservation and momentum conservation. Would you please go back to that slide,
Sure.
please?
Let's see, it's going to take a bit, but yeah, we'll get back to it. I'll beat you. Yep, Gianluca will get it, I think. Are you sure you wanted to see that slide?
Well, actually, the question I was about to ask you actually is on the left side, which is invisible here. I guess I thought I can skip the question. It might be my misunderstanding or there's a small confusion in
Thank you.
in their notation.
Yes.
For the momentum equation on the left-hand side, the time derivative,
Yes.
and I assume you have the material derivative or the total derivative for the velocity instead of just the time transient component. You have both.
It's a total derivative because
Total derivative.
it's a Lagrangian method, so we don't have to compute the convective
Right.
terms.
Right. Okay.
Yes.
Thank you.
Yep.
Regarding the SPH, as you mentioned, it's a weighted interpolation method instead of weighted residual or variational method. And how do you plan to improve the accuracy of modeling using SPH? Besides, introducing more particles, using more particles, please.
So there are a variety of issues in that question. So there are some practical ways that we improve the accuracy. For example, everything is based on particle position. And when we do problems, like we're doing some work on fish passes for dams and river flows and lava flows, that you have very low aspect ratio problems. And so when you're looking at the difference between 2 particles that are very far away, then you have problems. And so what we have is a homogeneous accuracy method where we set up a whole variety of origins so that we can improve the position information for the particles. One of the problems with SPH is quite often we have pressure fluctuations because of the fact that we solve the equations numerically with a given arrangement of particles, and then we advance the particles in time, and then so that introduces kind of a disequilibrium as it goes forward. And so there are ways to treat that, either with shepherd filtering, some people use. There's a whole school of thought now to add diffusion terms into density equations, which we're trying now, and that cleans up the pressure fields tremendously without filtering. So that's another accuracy and affects the stability as well.
You know, as a pioneering expert, do you think it's possible to implement some, mathematically implement some projection like Galerkin projection or least square projection to improve the accuracy? Is it possible?
I think it's possible. There are a lot of people doing lots of different ways to solve the problem. So using Riemann invariance is one way. Their projection methods are being used, lots of different integrations and times like Runge-Kutta and so forth, so improving the accuracy and the time steps. So there's a whole variety of how you can improve or change the time stepping in time, in the integration in time.
Great. I have the questions regarding the GPU computing.
Yes.
Would you please comment on the pros and cons of GPU computing versus the conventional CPU, MPI, OpenMP, or the virtual parallel machine? That's the first question. The second question is, in your opinion, what do you think the limitations in the GPU technique, please?
Okay. Well, so in answering the last question first, the limitation is the amount of storage on the graphics cards. That's the biggest limitation. I think the disadvantage of GPU computing is that you have to rewrite your code specifically to take advantage of the GPU. Rather, you can use the GPU as a math coprocessor in the old days of computing, such that, if you want to invert an array, which we don't do that, but if that's what your method calls for, inverting array, you can pass all the data up to the GPU, invert it, and send it back down and use it in that fashion. But that's very clumsy because there's a certain bandwidth to get the information to the GPU card and then back. And that's much slower than passing information around on the GPU. So it's best to do all your computing on the GPU. So the disadvantage is that in our case, we use CUDA, which is the NVIDIA language for GPU computing, which is C++ extended for graphics cards. So you have to learn that and you have to use that. There are Fortran compilers that natively include the calls for the graphics card. So the Portland group, for example, does Fortran. But still, to do it right, you have to rewrite your code. And so that's the drawback with legacy codes, is a rewrite is necessary.
Thank you very much.
Sure.
Before turning to the audience, I'd like to ask Professor Yang's figures to ask a question, and then we can go to the audience.
Well, first of all, thank you, Professor Dalrymple, for your inspiring lecture, and of course, inspiring coastal engineers for generations now. I'm happy to have also provided some help for improving the SPH method by playing video games. I think that was very nice that you
Thank you,
that.
thank you.
It makes me feel much better. I have a more a general question, since I'm interested in also some sediment transport issues. With that method, I mean, you showed some very interesting wave characteristics down to the detail that you can model. How could you push the frontier of basically modeling sediment transport phenomena in the surf swash, so maybe also overtopping, overwash phenomena like sheet flow mechanisms or inception of grain motion? If you could elaborate just a little bit on that before we turn it over to the audience, that'd be great.
So the problem with sediment is the problem of sediment transport, which we all know is really hard anyway. That's why my whole career has been in fluid mechanics. But the problem of doing the sediment is you have the suspended flow, you have the bed load, and they have to be treated differently. I did have a student, Shanzhou, who did suspended flow coupled with waves. So once you have the GPU particles operating, you can solve any number of equations that you like. And so in addition to the ones I showed, you can add an equation for concentration of suspended sediment, include the fall velocities and so forth. And what we had was a pickup function on the bottom based on the bottom velocity or the bottom stress. And what we would see is as the waves go by, you would see sediment being lifted off the bottom and then trained into the flow. And so that works out well. We had to do some tricks with upwind differencing and things like that. But we didn't treat the bed load problem, which for sheet flow and sort of swash motions, you'd have to have that as well. If you look at the microscopic problem, you can actually treat each individual sand grain and track sand grains and sort of a discrete element model coupled with SPH, and there are people doing that kind of thing. But then you're looking at the real micro scale, and then how do you integrate that to a beach? So, you might be able to do some multi-scale applications doing that. But so, in fact, with our open dynamics engine, we could put in, well, you saw the dam break problem with a ball banging into the wall and other objects. So we could just put a whole bunch of spheres and look at the interaction to see what happened. But in terms of really looking at an eroding beach or something like that, including all of the sediment physics, that's not been done yet. Let me put it that way.
Thank you. So we'd like to turn it over to the audience if there's any questions from the audience for Professor Dalrymple.
Please.
Well, in your beautiful lecture, you mentioned turbulence, and my little question is this. Well, it is well known that in aerodynamics, we have also a role played by chaos, implying fractals, Mandelbrot's mathematics. And my question is, this is a sort of area which is quite embarrassing because it was decided to be some of the most fascinating but also complex areas in physics. Is involved chaos, are involved fractals in hydrodynamics, in this area of hydrodynamics, in turbulence, like in meteorological aerodynamics, yes, as it is well known?
Yes, I think the short answer is yes, in the sense of in hydrodynamics, we would have the same thing as in aerodynamics. We would just change the fluid, right? So the turbulence behaves similarly. Everything I showed, we can look at things like the kinetic energy in the fluid and the frequency ranges at which it occurs. But it's a very deterministic chaos or deterministic turbulence that we're integrating in time to see how it evolves. So I don't use anything with chaos theory with what you saw today.
Professor Dalrymple, thank you for your talk. And I do have a question with your example before. It's like a jet flow that go into a flow. In this simulation, I think, because it seems like you bring more particle into the computational domain, but when I do my project, it's like initially you need to specify how many particles are in this computer domain, right? But
Yes.
it seems that in that example there, you have more particles just go into the flow.
Yes.
So,
So there's-
I was wondering, how did you handle that jet going into the
Yes.
flow?
So there's lots of ways to handle it. The real way is to introduce new particles through a jet. In this case, it would have been a plane jet. And it turns out you can bounce a plane jet, but you can't bounce a round jet. So water waves are plane jets. But you should just introduce an inlet and then someplace else have an outlet so that you create and destroy particles. But I didn't have the inlet condition, so what I did was preloaded a ramp of particles and then gave them an initial velocity and just shot them down the ramp into the fluid. So there was a finite number, so if I'd run it longer, you'd see the jet stop. Yep. Thank you.
Question with respect to the V&V, the verification and validation
Yes.
of this class of models. What's being done in that respect?
There's a whole slew of researchers, including ourselves, that are working on validation test cases. So we have a test suite where we look at problems like flow around the sphere, flow around the cylinder, laminar flows in pipes, and so forth. So the standard classical kinds of test cases, and then we're looking at a lot of laboratory experiments with waves and other phenomena, so for validation. And there's a lot of mathematics going into convergence and consistency and so forth. So doing that as well.
Okay, Tony, I'm here.
Hi.
So my question is, if you wanted to basically do deformable bodies, what would be the first pass you would take?
So there is I've been working with somebody in France and modeling Posidonia seaweed. And so basically what he did was make a finite element model of the seaweed and then put it into the domain and couple the two. And so that's sort of the first approach. But you can build solid objects with either something like Open Dynamics Engine or do it by hand, but you can create the moving objects in the model itself if you wish as well. So there are people doing that kind of thing and having some success.
Yes, thanks very much for an interesting lecture. It was really revealing to learn that this has its origins in celestial mechanics. And I guess that leads me to an entirely self-serving question, which would be, if it started in celestial mechanics and you're using it for fluid mechanics, is there the possibility to use this in solid mechanics to model a solid-like behavior? And I think there are some groups who are attempting to do this. What are your thoughts on?
So it's just simply changing the equations of motion and your constituent equations. And it's being done. So a lot of the original advances were done with impact problems, projectile impact problems in the 70s and 80s and 90s and so forth. So there has been a lot of work in solid mechanics. It's just change your pressure terms out and so forth. Redefine a few variables, but it's readily done.
Question here.
Yes.
Both yesterday morning's talk and your talk make me think that there's such a steep learning curve for a researcher who wants to adopt these methods, which are very broadly applicable to our research. And it looks like we always need to have a PhD student or postdoc to learn a lot and then apply the techniques to our problems. Is there any way you think we can change our curriculum a bit to teach our students so that they can learn these new powerful methods quicker? Because it seems to be very broad-based. You talk about upwing method, convergence, and most of our civil engineering students do not learn all these things.
Yes.
So looking at those powerful, beautiful techniques, I feel I wish that we have more students who can handle these.
Yes. So 2 parts to that. One of the reasons we make the code open source is that we don't think that any student should have to reprogram SPH from scratch. And if we're going to spend all our time making a model, you shouldn't have to have a student redo everything we've done for the last 5 years. So the intent is to put it out open source and have people use the model as a tool. So all of that, the work with the impact of the space capsule was done by a master's student. And he did learn enough C++ to change the inputs and so forth. So it's possible. The second part, in terms of the curriculum, you're right. I think 10 years ago, somebody told me that, why aren't you academics teaching parallel computing? And it's still a good question. And so I actually volunteered next semester to teach a course in parallel computing. So, with GPUs.
All right, I think that we run out of time. Yeah, let's thank Professor Dalrymple again for his inspiring lecture.